started? So in our last meeting, if you remember, we talked about multiple methods to, when we design a sequential circuit, there are multiple methods that are different than the analysis, and they can come handy at times. For instance, state reduction is one of the one of those methods that might come handy. In the analysis, you usually are given the circuit, right? The circuit is provided to you. So you would start analyzing the circuit, but the circuit is already optimized for it because I'm giving you the circuit. However, when you do the design, you are the engineer who has to come up with the circuit, right? So that's your duty, that's your responsibility to come up with the best circuit ever. Of course, given the constraints of the design, such as flip-flop model is going to given to you. For instance, you have to use D flip-flop or JK flip-flop. That's a constraint, design constraint. Or maybe there might be some other constraints like gate delays, for instance. The latency of the circuit must, for example, satisfy those criteria, for instance. Those type of constraints can be given, before you start designing your circuit. And your responsibility is to meet those goals, those objectives, okay, dictated by the specification. All right? So that's why we learned about, one of those things that we learned is the state reduction problem, because, once you read the specification, you may come up with a state diagram that represents that specification. However, that state diagram may not be optimal. Okay? In other words, you may be using the number of states in your state diagram may be more than needed, okay, more than sufficient, more than enough. So therefore, we introduced that state reduction, okay, method that reduces the number of states. You came up with, for example, 10 states. I think in our example we had 8 or maybe 6. I don't recall right now exactly, but it was about 7, 8 number of states. And then we used our state reduction technique to come up with 4 states, right? And 4 state means 2 flip-flops. But you have got 5 states in your finite state machine. That means you need to use 3 flip-flops, not 2, right? Because the number of possibilities by just using 2 flip-flops is 4, okay? That's why. So in order to reduce or minimize the number of flip-flops, then you may want to employ such a technique to reduce the number of states. That was one of the things. The other problem was state assignment problem, right? Once you come up with a state, for instance, let's say A, B, C, D, then how are you going to represent A, for example? There is no A in the digital domain. You only have, binary numbers, right? Zeros and ones. Therefore, you have to map these A, B, C, D to a number, to a binary number. Okay, this is called coding or encoding. So we're going to be encoding these symbols. And the most straightforward, or maybe the conventional method, is to map these A, B, C, and D to 0, 0, 0, 1, 1, 0, and 1, 1, right? Just the most conventional methods that we use 2 bits to represent 4 symbols. Okay? How about we map A instead of to 0, 0, we map A to 0, 1, for example. This might be another alternative mapping strategy. Instead of doing this, you may want to do this. A to 0, 1, B to 1, 0, C to 1, 1, for instance, and D to 0, 0 maybe, right? That might be another strategy using 2 bits. Or you can even come up with different alternative strategies, such as using 3 bits or 4 bits instead of representing them using only 2 bits. So for example, you may want to represent A with 0, 0, 0, 1, B with 0, 0, 1, 0, C with 0, 1, 0, 0, and D with 1, 0, 0, 0, right? This is another alternative strategy. However, this uses, as you may guess, 4 flip-flops rather than 2, right? Because now you have to store 4 bits. However, you're using 4 flip-flops and 2 flip-flops here. However, most of the time, you use less combinational logic here and more combinational logic here. There's a trade-off actually between them. You can design the same exact circuit. So this state assignment problem is not so straightforward. That's what I'm trying to, give you as a bottom line message today. Okay? This state assignment problem is not a straightforward task. Because once you're doing this state assignment, this is going to change your combinational circuits. Remember the generalized depiction of a sequential circuit? We usually have a state register here, right? State registers. These are flip-flops, by the way. I call them register. And there are front and back end, right? For example, this is back end combinational circuit, and there is a front end combinational circuit. Remember them? And we said that this is input, right? And we said that this back-end combinational circuit can use, it has to use state register output values as well as the input. It can use them. And then we call it Mealy, right? The Mealy circuit is, the output here, is a function of state values as well as the input, okay? Or maybe not, entirely the input, but maybe, a function of input, right? That might be a possibility that can go through that front-end combinational circuit and creates a value to be used by the back-end combinational circuit, and we got an output, okay? The state registers are actually used in your front-end combinational circuit to generate the next state, okay? And this is a must for both Moore and Mealy circuits, okay? If the output is not a function of input, then we call it Moore. If output is a function of input, then we call it Mealy. Okay, that was the distinction between these two machines. But however, this arrow here is a must. In other words, you have to actually calculate the next state through certain combinational circuit. Okay? This is just a definition of being sequentiality, that you have a sequentiality in your circuit design. Go ahead.
For the mappings, we said that the two flip-flops cause more complex logical.
Conventionally, typically, this requires some gates in the back end and the front end. Okay, most of the time. However, when you go to this type of design, this type of assignment, that would generate more registers, right? Because here, for example, you need 4 flip-flops. So the state register complexity increases. But the gain that you get due to this is the reduction in the complexity of the back end and front end. Typically, for the same design, for the same circuit, when I'm talking about same, I say I want to express that it's the same specification. Okay, given the specification, the same specification, you've got 2 design options. You want to increase the complexity of the state registers by putting more flip-flops and reduce the complexity of the front end and back end, or you can minimize the number of state registers, increase the complexity here. And which one is better? Well, it depends on the application. Depends on the application. Okay? And we'll actually have an example for these 2 particular assignments, by the way. For example, if you want to come up, which I'm going to talk about today, this is the majority of the class will be based on, specification and drawing the state diagram. Because once you draw the state diagram, the rest is just standard. Okay, standard, which I actually started discussing this in our last meeting. I'm going to continue that discussion by showing you, because the slides were designing the circuit using D flip-flops. Today I'm going to design it using JK flip-flops as an alternative design. However, most of the problem the students are facing in their sequential circuit design problem, when they're dealing with a sequential circuit design problem, is the transformation of an English description of the problem to the state diagram representation. Okay, that's why I want to focus on this particular challenge that students most of the time are facing, in the exam or in the homeworks. Okay, I want to develop that kind of feeling in you when I express my, design criteria or an couple of English sentences describing what your circuit is ought to do, then I want you to draw the state diagram or finite state machine representation of that problem, easily. That's what I wanted to, give you today. All right? That's the major objective of today's class. Okay, major learning outcome, let's say. Okay, but just know that this is an important actual decision that we're making. Okay, because that changes the complexity of the circuit. And I'm going to, as I said before, I'm going to give you an example specifically that will do this type of assignment and this type of assignment for the same specification, which is the counter. Okay, counter example, which I would want my circuit to count the following numbers: 0, 1, 2, 3, and then go back to 0. 1, 2, 3, and then go back to 0. Okay, this actually goes on and on and on and on without any, stopping. This is a kind of a counter, but it goes back to the beginning and then counts again. Okay, and the time between these numbers is, of course, the clock period, right? Clock period. You can, of course, introduce inputs to stop this counter or change the counter, for example. It can count only even numbers, for instance. You can think about any type of design, okay? But this is the most basic counter you can ever have. So this, of course, is specification of a specific problem, right? I want you to design a counter. And that can count up to 3, okay? And then it goes back to 0. Why it's up to 3? Because I assume I have 4 states. Okay? And each one of them represents one of those numbers. Okay? 0, 1, 2, 3. And then come back here. Or maybe 0, 1, 2, 3. And then go back here, 0, 1, 2, 3. So you may actually have the following simple state diagram for this particular purpose, right? Okay, so you can actually go here without any inputs, right? There is no input. It just, visits those states on and on and on and on. And that's the state diagram, in fact. There's no input, there is no output. Actually, there are outputs. Outputs are the numbers here. So, but what I'm going to do, I'm going to just erase those, A, B, C, D, and then use this mapping. Let's say, this is my mapping. I'm going to just say 0, 0, 0, 1, 1, 0, and 1, 1. This is my C now, okay? B, C, D. Oops. Okay? This is my state diagram, finite state presentation of the counter example. All right? And are there any outputs? Of course there are outputs, but there is no input. Okay? This is actually generating an output without having an input, okay? Which is a possibility, by the way. And now I'm using only 4 states to represent this, right? And only 2 flip-flops to design this, okay? We can go ahead and design using our standard approach a counter using 4 states like that. Or you can use this assignment. Okay, this assignment to create a counter, okay, using those 4 states now. In other words, instead of doing this kind of mapping, you can actually do the following kind of mapping: 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, and 1, 0, 0, 0. That's another possibility, okay, doing this type of mapping. However, you shall see that using this mapping, you will not use any gates. 0 gates. 0 gates. In other words, there is no front end, there is no state back end combinational circuit. This just flip-flops. Okay, just flip-flops. This is called ring counter, by the way, which we will cover later on, maybe next week, when we discuss registers and counters. Okay, I'm going to give you the details of why this is not using any combinational circuit. This is called ring counter. This is standard counter, okay? It's a standard counter, and you can, of course, as I said before, introduce inputs and outputs to control this counter, such as you may want to have an input, for example, to count forward and backwards, right? A single bit. We can have a single bit. If that bit is 0, we can let the counter count in forward direction. 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. Whenever you make that input, or change or switch from 0 to 1, then the counter goes backwards, okay? For example, you did that at that particular point in time, then it starts counting downwards, okay? Now it goes 2, 1, 0, 3, 2, 1, 0, 3, 2, 1, 0, okay? That's, for example, another design that you can change the direction of counting. All right, anyway. So there are 3 ways. We've got a question?
Yes.
Go ahead.
What's the difference between the standard counter and the ring counter? This one has 4 flip-flops.
4 states, and that 2 states. I'm sorry, 4 states, but you got 4 flip-flops to represent that state, 2 flip-flops to design that state, that circuit.
And because of that, the ring counter doesn't have any front end or back.
It doesn't use any gates, okay? It's just empty front end and empty back end in that general description, okay? And by the way, one of the things I think I want you to realize that we usually wrote input and output on top of these arrows, right? So there is no input, but the outputs are not also written because outputs are actually states, right? Is this a Mealy or Moore circuit? Moore, right? Because outputs are just outputs and also they are states. Okay, that's why if it's a Moore circuit, then we wrote the outputs to the states, okay? And if there is no input, we don't use those arrows. I mean, we don't put anything on these arrows. If there are inputs, okay, for example, X might be 0 and 1 for backward and forward counting, right? So we can actually say, okay, input is 0, let's say, to do the forward counting, and input is 1 for backward counting, right? But that's it. We don't put output right here, okay? For example, we don't use this, okay? Or maybe in this case it's 0, 1, right? Output is 0, 1. So we don't use this kind of notation for Moore, okay? So you can actually, when you just look at the finite state machine representation of a circuit, you can immediately say it's a Moore or Mealy. Because in the Mealy circuit, we usually use this type of notation, okay, to indicate that the output is not only a function of states, but also a function of input. That's why we actually wrote it separately. However, in the Moore circuit, you don't have to do that because those states actually is your output. Okay? So you don't need to write them twice. Okay? You only put the inputs. Okay? If there is an input, of course. If there is no input, you don't put anything on the top of the arrows. Okay? That's another, for example, thing we realized to distinguish between the Moore circuit and a Mealy circuit. Their state representation is actually different. I mean, these state diagrams actually typically drawn differently. Okay? Anyway, coming back to our example, design example. In our design example, if you remember, we did have a sequential logic that detects a sequence of... by the way, I want to talk about 3 different designs before I, move forward with maybe I can use the other part of the board with a different color. Before I will move on, I want to actually make sure that we know what type of sequential logic can be created. For example, this type of sequential logic here, you see standard counter, for example, there's no input, it just generates an output, right? So there are 3 types of objectives when you design a sequential circuit. First, you can be used to generate bit sequences. Oops. Okay? Maybe one of the objectives might be generate bit sequences. That is one of the objectives. And this standard counter does exactly that because it generates a sequence of bits, right? In other words, this 0, 0, corresponds to 0, 0. This is 0, 1. This is 1, 0, 1, 1. And then this is 0, 0, 0, 1, 1, 0, 1, 1. You see, it's just a sequence of bits that are generated without even providing any input to the circuit. It just generates automatically. Okay, so that's the first example, generate bit sequences. The second one is detect bit sequences or bit patterns. Detect bit sequences or bit patterns. Okay? This is an R. Patterns. Okay? What is that? That is the example that you have in your slides. Okay? This detect a specific sequence, for example. 1, 0, 1, 1. You are given an infinite number of ones and zeros, and what you ought to do, you detect a specific sequence. For instance, 1, 0, 1, 1. A specific sequence. You basically have a window, of 4-bit long, and then you move that window over your sequence. When you have a specific sequence that you want, for instance, 1, 0, 1, 1, then you output a 1. If you don't detect any specific sequence, such as 1, 0, 1, 1, then you output a 0. Okay? That's a sequence detector, for example. That is very commonly and often used in digital circuits because people want to synchronize. In storage system, there's a synchronization system, for example, or communication systems. There's also always a synchronization methodology that use a specific sequence to synchronize themselves with input and output relationship of the receiver and transmitter. Okay? So that's why sequence detection is very, very important. Finally, they can be used to transform sequences. Okay? For example, a serial ladder. You have got two inputs that are going into your sequential design, an adder. Okay? In other words, if you remember, we did have, for example, 4-bit adders, right? For example, this one and 0, 0, 1. So we know how to add them, right? So in the serial adder or sequential design of the same adder type, there are two types of approaches here, right? We covered. One of them was a ripple adder. The other one is a carry look-ahead adder, right? These two are combinational designs. I'm talking about a sequential design where we have the carry information stored in a flip-flop, so it actually holds that carry value but changes. At each clock cycle, right, we process these 2 bits, and then we keep that carry for the next stage, and then in the next clock cycle we process these 2 bits with the carry, and then we update the carry and then move on to the next stage in the next clock cycle, and so on and so forth. This is called serial adder, and that serial adder can be actually applied to any number of bits, not just 4 bits, right? That transforms the information, right? There are 2 sequences of inputs that goes into the serial adder, and serial adder generates a single output, that is sum, right? So that is a transformation, which I'm going to also have details on the serial adder later on, okay? I'm just giving you an example of transforming sequences using sequential circuits, okay? These are the 3 main classes of usage of sequential circuits. Though that one that I just talked about, standard counter, is an example to the generation of bit sequences, okay? And I'm going to now talk about detection of bit sequences, okay? For example, this is from the handout, by the way, okay? For those of you who are wondering about the answers to the handout, that I received many emails about that. So I'm actually solving them. I mean, not all of them, but most of them in classes. So you can check the videos on these questions. Okay, so one is the, let's just suppose that our circuit is supposed to find the following sequence. 1, 0, 1, 1. Okay? A sequence to find. Okay? A sequence to find. So, let me just give you the example what this circuit is supposed to do. I'm going to give you an input, Okay, and input is like almost infinite. It's just the serial ones on zeros. 0, 0, 1, 1, 1, 0, 1, 0, 0, 1, 1, 1, 1, 0, 1, 1, 1, 0, 0, maybe 2 zeros. 0, 1, 0, 1, 0, 0, 1, whatever. Okay, it just goes on and on. And what I am supposed to do with this circuit, it's going to accept this as an input sequence, it's just a single bit, okay, and it's going to process information at each clock cycle 1 bit at a time, okay? In other words, it's going to just put a window on the beginning. Let's suppose that this is the beginning, okay, and this is goes on and on. It's going to actually put a window here. It will check whether this is a valid sequence that I'm looking for. Is this? No. So it's going to output a 0. Okay? And it's going to move in the next clock cycle to the next window. It's going to look at this sequence, 0, 1, 1, 1. It's going to output a 0 because it's not what I'm looking for. I'm looking for 1, 0, 1, 1. Okay? And then it's going to move to here. It's another 0. Move to here, 1, 1, 0, 1. Is this 1? No. So it's going to put another 0. And then I'm going to put this one, 1, 0, 1, 0. No. 0, 1, 0, 0. No. And then I'm going to have 1, 0, 0, 1. No. And then 0, 0, 1, 1. No. No, no, no. Until I hit here, right? Until I hit here. 1, 0, 1, 1. Okay? This is where I'm going to have a 1. Okay? And then, of course, you move on to the next one, which is again a 0, and then another 0, blah, blah, up until you hit another 1 here, because this is what one of those sequences you're looking for inside this binary stream of bits. Okay? Of course, one of the things you may want to explore is the following example. For example, it goes on, and you hit the following, for example. 1, 0, 1, 1, let's say, and then 0, 1, 1. Okay, what happens in this case? Well, you have this window, 1, 0, 1, 1, and that's valid sequence. If you move on to the next one, you got 0, 1, 1, 0, which is a 0, and then you got 1, 1, 0, 1, which is another 0, but then you have 1, 0, 1, 1. That's going to produce another 1. But those windows actually overlap with each other. Okay? So you might want to actually put some, thinking in that, because those windows, even though they overlap, they can actually have a sequence. Okay? Keep that in mind. They don't need, all these windows need not to be separated. Okay? So when you draw your state diagram, which I will right now, I'm going to take this into account. Okay? That's very, very interesting observation. Okay? For instance, if I give you a sequence of the following form, 1, 1, 0, 1, 1, you always have to think, this might be the beginning of another valid sequence. Right? As this one have been the beginning of another valid sequence in this example. Right? So in other words, the prefix of this sequence might be the suffix of another valid sequence. That's what I'm trying to say. You have to keep that in mind when you draw your state diagram. Okay? That's also the tricky part. When you design a state diagram of a circuit, that's why I wanted to first emphasize this before I draw the state diagram right now. Okay? Okay, so let's just draw the state diagram that detects this sequence. So first of all, there are multiple ways. Okay, there's no unique way. But I'm going to just throw one for you. I'm going to start with a state, and state transitions, okay, in my design, of course, state transitions will always be possible, will always become, proper when I see this sequence. In other words, I'm going to transit from one state, this state, to this state when I see a 1. Okay? So input must be 1 in order to move from this state to this state. I haven't done the state assignment yet. Okay? This is A, this is B. I haven't done the state assignment yet. Okay? But I'm going to just make sure that I transit from one state to another if I see a valid bits of the valid sequence, okay, that I'm looking for. So this is the first transition. Is this recording?
3 seconds.
I have got two states, and I move from this state to state when I see a 1, and then I have got another movement or transition from this state, B state to C state when I see 0. Okay, let's just write it down. And then I see another state transition when I see 1. Okay, and I'm going to, of course, I have to think about the outputs as well, right? Because when I see for the first time a 1, I should output a 0, right? So I'm going to have a 0. And this is also 0, and this is also 0. Okay, I haven't completed my sequence yet. But when I see 1, may have the first bit of another valid sequence. Okay, so that's why I'm not going to draw another state. I'm going to do the following. Why is that? Why am I not coming back here? Because this 1 is already have seen. That's why I'm actually coming back to B. Okay? And of course, input has to be 1 for this to happen. And output is, of course, 1, because I detected a sequence of the following, 1, 0, 1, 1, of that following pattern. Right? So this output must be 1. This is the most crucial part of drawing the finite state machine. All right? Because now you actually completed a detection path. This is the detection path, actually. In order to detect that 1, your input has to follow the following path. It has to go to A to B, B to C, C to D, and D to B and back again. Okay? In that case, then, you have got the detection pattern. However, this is not over. We're not over, because we've got other possibilities. For example, when you're in the initial state of A, and you see a 0, you're not going to move anywhere. And output is 0. Okay? So when you have in the beginning all zeros, you have to wait. You're going to have to be in the initial state for as long as you've got zeros. Okay? Okay, let's move on to the B. So you've seen 1. You've seen 1. And you don't see 0. You see another 1. What am I going to do? Should I go back?
Go back.
Who thinks that we should go back? Raise your hand. Who thinks that we should go back to A? If I see a 1. You, all right? A couple of people. How about others? Do you think that we should do what? We should stay?
Yes.
We should stay.
Yes.
We should stay? We should stay? Everybody agrees? Because yes, we should stay. Why? Because that 1 that you're seeing might be the first one of this pattern. That's why you don't need to go back, because this transition represents the following physical phenomena. It basically tells you that the first one is arrived. Okay? Then, when you're here and you don't see a 0, okay, that's the second bit of your pattern. You see a 1, but that 1 might be the first one of another sequence that is valid. Okay? That's why you stay here, but output, of course, is 0. Okay? How about C? When I come here C, and I see it, I'm in state C, I know that I am in C. And I don't see 1, I see 0. What should I do? Where should I go?
Go back to B.
B? So that means actually, when I'm in C, that's what physically happens. I saw 1, I saw 0, okay? And then I saw another 0. Right? That's what it means. Okay, so what should I do then?
A. Back to
I think I should go back, but which state I should go back?
A.
Who thinks A? Who thinks B? B's? Okay, B. C? Is there any C's? D's? Okay. The answer is A. Why? Because this 0 is not the beginning of this pattern. I have to start actually counting this pattern from the beginning, because this is 0, not a 1. It didn't happen for B, because in the B, we have a 1, and that 1 might be the beginning of a valid sequence. That's why we stayed in the same state. But for C, that's not the case, because in order to move from C to D, I need a 1. So if I have a 0, then I have to go back. Unfortunately, that 0 is not the beginning. That's why. Okay? So I have to go back here, and my input is 0. Output, of course, is 0, because we haven't detected anything. All right? And finally, D, right? In the D, if I see 1, I complete the cycle. Okay? If I see 0, That physically means that I've seen 1, I've seen 0, and I've seen 1 again, and then I've seen 0. What should I do?
Back to CC.
Back to A? Who thinks A? B? You think B? Okay. C? Well, most of the guys B. Okay. So think about. So look at the sequence. Could this be a prefix of this sequential pattern that we're looking for? Yes, because you see 1, 0 is actually the prefix. Okay, of this pattern. So therefore, I have to go back somewhere that will ensure that I've seen 1 and 0 already. 1, 0, so therefore I have to go back to C. Because that C ensures that I've already seen 1 and 0. Okay? So that's why, if this is a 1, I mean input is 1, then I output a 1 and I complete the cycle. If I see 0, I output a 0, but I go back to C. Because I already have seen 1, 0. Okay, that's what this means. Okay, so if you design your state diagram this way, then you take care of these, overlapping windows problem. Okay. Question?
Can you repeat the last part, please?
This one, transition to. Okay, so you have to think when you do all these diagrams like that, you catch this overlapping window problem also. Then you have to think about these states. When you are in those states, you have to think in terms of physically what's happening. For example, when you're in A, that basically means that you don't have anything in memory. You're just waiting. It's the initial state. That's the beginning. The life starts. Okay? When you're in state B, that actually means physically something. That means you already have seen a 1 in the input. Okay? That's why you're actually, taking into your memory and counting whether this pattern appears in the input or not. Without that memory here, there's a memory apparently. Without that memory, you wouldn't be able to figure out that pattern. That's why we need a sequential circuit in the first place. Okay, so when you come here, that basically means the input is they already have seen a 1 in the input. That's what this means. C means I have already seen a sequence of 1 and 0, because that becomes a sequence now, right? 1 and 0. D means I already have seen 1, 0, 1 in the input. Okay? So let's come back to your question. When I'm in D, that means I've already seen 1, 0, 1 already. Now I'm thinking about the next bit. Now, if next bit is 1, then I complete this cycle actually. So the pattern is complete. That's why I actually go back to B. Okay? But if I see 0, that means I have gotten the input 1, 0, 1, 0 sequence. Now I'm thinking about this sequential pattern that I'm looking for. In this sequential pattern, I see in the prefix, the beginning of the pattern has a 1, 0. But this, when I see this last 2 bits, 1, 0, not the 3, 1, because these 3 1s is not fitting in the prefix of the pattern that I'm looking for. So that's why I'm looking for these 2 bits, okay? If I didn't have 1 bit, for example, I can start with 1 bit. Is this matching? No. Then I look for 2 bits. Is this matching? Yes. That's why I say, okay, I already have seen these 2 bits, 1 and 0. But that is already represented by one of our states, which is C. Then I should go back to C. Because I already have seen 1, 0 in the input.
Search for another.
Yes, then you continue searching for other 1, 1. Okay?
Is in every state, the previous state is the previous state's output is the second state's input?
Are you talking, when you say state, do you mean those states?
Yes.
Yeah, I mean, those states actually, this is Markovian type of, discrete Markovian model. What you're seeing is just, these transitions can only happen at specific time instance, which we call clock signal, right? The clock transitions. So when you have a rising edge or a falling edge, you have those transitions. There's no input-output relationship here because there's nothing in process here. It's not like flip-flop processing something. This is a logical diagram. It's all logical. And what I'm saying is that this describes a problem. This Markovian, okay, representation using states is describing a specific problem. Okay? We haven't solved anything yet. This is a problem actually. This is basically telling us what the system does according to the inputs and what are the outputs, corresponding outputs for those inputs. Okay, that's it. There is no processing. Okay?
Okay, so for example, for A, if input is A, output is 0, right? What if input is
Input is what? 1.
Input is 0.
0.
Yes, so is it maybe B 0?
So what you're seeing on those arrows actually is an input-output relationship. When you see a 1, when you're in state A, okay, system assumes a state. Actually, system jumps from one state to another. Okay, so for at a given time when this circuit is operational, when you arrive, when you look at the circuit is in one of those states. Okay, if it is in C, for example, and you accept a single bit of input, if that input is 0, this state diagram says that you have to move back to A and output a 0 and then assume your next state is A. If the input is 1, then this state diagram says that you have to move to D. Your state moves or transitions to D, and input is, if input is 1, and you have to output a 0.
Is it like if-else, if-else conditions?
Say again?
Is it like if and else conditions?
Yeah, it's like that, yes. I mean, depending on the input, if input is 0 or 1, you choose, one way or another. You change your state to either A or D. Okay?
Okay.
So it depends on the input. It's a function of input, of course. Okay? Okay, so I actually now recommend you guys, in order to digest this material, I would strongly recommend that you draw the same state diagram using other sequence patterns, such as 1, 1, 0, 1, 1, for example. That might be a good example. Or maybe you can choose 1, 1, 0, 1. Those symmetric patterns are very interesting because that creates those overlapping problems. Okay? But for instance, the following, let's say 0, 1, 0, okay, it's not very interesting. It's kind of easier actually because there is no window type of thing happening. But you can still have for this particular one. For example, if you got this repeating pattern like 0, 1, 0, 1, 0, 1, 0, 1. Okay, in this case, this is your window, right? If you move to here, it's not your window, but that is your window, right? So there's this prefix and suffix thing also happens for this 3-bit long pattern. Anyway, I think if you draw a couple of those, you will get the idea. Okay, it's not too hard. Anyway, so once you know the state diagram, you see there are 4 states, and then I'm going to talk about the design of this particular circuit. Since we already have an example in the slides, I don't want to really repeat that example. It's on slides. You can just walk through it yourself. You can learn it. I'm going to design this circuit instead. Okay, would that be all right with you? Okay, let's just focus on this example. See if we can design it. Is this a milli or more? What do you think? Milli, right?
Milli.
Why?
But there are 2 reasons. First of all, I actually just said that by just looking at the arrows and input-output relationship, you can actually immediately say that output is a function of input, right? Because it depends on the input. If you don't know the input, you cannot say whether you go from A to B or you stay in A, right? It depends on the input. So if there is a dependence on the input, then it's a milli circuit, okay? Okay, so now, let's design it, okay? I'm going to keep that diagram because that is essential. Okay, once you have a state diagram like this, okay, then you are ready to design your circuits. One of the things you realize, by the way, that we actually have drawn this state diagram knowing the fact that those windows might be overlapping with each other. We actually did a lot of optimization here by just observing this. You can actually come up with more states, like 5 states, 6 states, and do exactly the same thing. That's also fine, but you have to apply the state reduction technique to reduce the number of states to 4. Okay? So here is the gist of the main message. is that you cannot reduce the number of states from 4 to any lower number, unfortunately. So that's why I'm going to skip the reduction step, because this is already optimal. And I'm going to now do the state assignment, which I can actually already do here by assigning, as I said before, conventionally we do this, 0, 0, 0, 1, and this is 1, 0, and 1, 1. Okay? Simple. As I said, this is kind of beyond the scope of this class. That's why I'm not going to discuss, alternative mappings, because it's just, outside the scope of this class. It requires a lot of more expertise to cover and master. So that's why I'm going to just apply, simple, minimizing the registers, number of registers in my circuit. So I'm going to have only 2 flip-flops here. Okay? Question? Good?
We knew that we couldn't simplify this further because of the sequence having 4.
Oh yeah. So there are only 4 bits. You have to keep track of these 4 bits already, and you have got 4 states. So apparently, you cannot reduce. Yeah, if you got 5 or 6, then you will need more states. Okay, but just try. Try. For example, for this particular example, you will say that I will need 5 or 6, but because of the overlapping stuff, okay, you may actually reduce the number of states here. Interesting. Okay? Just try this. Okay, let me just come back in. How many minutes do I have? Okay, 25 minutes. More than enough. So let me just cover the rest of the design. All right, so let me talk about the design. Because when you are talking about design, people have to tell you what you should use and what you should not use. Okay? Most of the designs are constrained by the cost. I mean financial cost. Okay? So you got the circuit elements that are not free, and you got some budget you can spend in your design, and this is the main force of industry. That means you try to minimize your cost of design. So therefore, I'm going to do the same thing. I'm going to just use JK flip-flops because they are cheaper. Okay? JK flip-flops, minimum. Because most of the time JK flip-flops are way higher price, sold at a higher price than NAND gates. Okay? So you can actually buy hundreds of NAND gates just to buy a single flip-flop. Okay? That's why. We're going to minimize the flip-flops. And that's why actually I use state reduction here to reduce the number of states, so I can use smaller number of flip-flops. Okay, so next thing you have to do from state diagram, you have to draw the state table. Okay, it's a state table. So I have 2 states. You see 2 states. In other words, 2 bits actually. That means 2 flip-flops. So there are 2 flip-flop outputs, A and B. I'm going to use them. So I'm going to use AT, BT. Okay? XT. That's my input, because I need a single bit for the input, right? Okay. And what is the output is YT. But I also have next state information, which is AT plus 1 and BT plus 1. And BT plus 1. And YT. That's my output. Okay? YT is my output, XT is my input. Okay, let's see. I'm going to put all these possibilities 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay? Okay, now, next thing you do, when you have 0, 0, in other words, you're in A, when you have an input 0, you got an output 0, and you stay in 0, 0. Okay? So therefore, if input is 0, output is 0, output is 0, and you stay in the same state. Okay? And when you have 0, 0, that means you're in A, and you have an input 1, okay? Then, as you can see, you move on to 0, 1, this is my first bit LSB, and this is my MSB. Least significant bit, most significant bit, in that representation of bits. So I move on to 0, 1, as you can see, which is the state B, and output is 0. If I am in 0, 1, which is B, okay, in this example, then when I see 0, I go to C. Okay, input is 0, that means I go to C, that's 1, 0. And output is 0. But when I see 1, I stay in the same state, which is 0, 1, and output is 0 again. When I'm in state C, which is 1, 0, and input is 0, then what I do? What do I do? I go back to A, right? So that is my A, and output is 0. And if I see 1, I move to state D, which is represented by 1, 1. And input is 1, output is 0. And finally, I am in D, and input is 0. I go back to C, which is 1, 0. And output is 0, of course, because I haven't completed the pattern yet. Finally, I'm in D, 1, 1. And input is 1, and output is 1 in this case. And I move to state B, which is 0, 1. Okay? You see there's a one-to-one relationship between the state table and the state diagram. Okay, but this looks much cleaner because that's what we're familiar with using the truth tables, right? So, this is the next phase. So what's the next phase from here? Do you remember? What do we do now? Counter maps. Absolutely. State equations. In order to find state equations, you need to find the counter maps. But the counter maps you need is 3. Because you have to first draw the counter map for the next state of the first flip-flop, the next state for the second flip-flop, and next state for the output. I mean, there is no next state for the output, but just output. Okay? So therefore, I'm going to draw for first flip-flop A. So this is 2 by 8, remember? Okay, you have to be really careful here. I'm going to put AB here and X here. Sorry, X here. Maybe I can put A here and BX here, okay? That's, I think, would be much more appropriate for me. 1, 0, okay? Remember those signs, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Okay, I hope you do. From the counter map, we're going to be using counter maps, you know, a lot of times in our sequential circuit design. Okay, so when I see here, so where is my ones? This is 1, 0. I've got 1, 0. So this is 0, 1, 0. I've got 1 here, and I've got 1 here, which is 1 and 0, 1, which is here. And I have got 1, A, B is 1, and X is 0. Okay? That's 1, my 1, right? And that's it. There are three ones, as you can see. And we can actually group these two. Okay? And unfortunately, these cannot be grouped. You know? So that's going to stay as is. But this you can actually minimize. This is actually given by BX. No, BX prime, sorry. And this is a B prime X, right? Okay. So now I'm going to write AT plus 1. AT plus 1 equals AT, because these are previous states. Or actually I can use, you know, the shorter hand notation, which I actually mentioned last time. I use A plus to mean T plus 1, okay? So that's my next state. A plus equals A, B prime X, and plus BX prime, okay? All right, so that's my first counter map. The second counter map is the second flip-flop, B. So I'm going to draw the counter map again for you. It's kind of messy. As I said, the rest is just standard, okay? That's why there's nothing interesting here. A, B, X, so let's just look at this. There are 4 ones, as you can see. This is 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. And I have 0, 0, 1, 0, 0, 1. And I have here 0, 1, 1, 0, 1, 1. And I have this one, 1, 0, 1, 1, 0, 1. And this one, 1, 1, 1. Right? If I'm not mistaken. So you see there's only one essential prime implicant. That corresponds, A is gone, B is gone, so that actually is X. So B plus is actually just X. Okay? B plus is just X. Okay, final one is Y, but Y is, I mean, I don't need to really draw the column map for Y because there's only one here, okay? So that corresponds to A, B, X. So Y equals A, B, X. All right? Okay, so one of the things I want to do with this, now we're done with the state equations, okay? So now you can use your background on Boolean logic, theorems, postulates to do maybe more minimizations, to do cross-optimization. In other words, maybe we can ask ourselves, do we have any common term, among these three expressions, these three outputs, okay? Maybe I can actually put here, I can actually rewrite this, AB prime X plus A prime, okay, BX prime, okay? So in this case, you see there is an A BX prime and A prime BX prime, right? So I'm going to just write this A B prime X plus A BX prime plus A prime BX prime. Okay, why did I do that? Well, there is no ABX, apparently, here. However, if I actually take in parentheses of A, I see B prime X, BX prime, right? So that is B XOR X, okay? And I see A prime, BX prime, okay? This is just an alternative. That doesn't really reduce the complexity, by the way, because it's just the same number of ands and ors. Use the XOR. But I just wanted to show it to you, okay? Other than that, there is no common term, as you can see, unfortunately. So now, next thing is to draw the circuit, the sequential circuit, right? After the state equations, you need to draw the state circuit, sequential circuit diagram. So in order to do this, of course, you have to decide on the type of the flip-flop you want to use. For D flip-flops, it's easy because input-output relationship is quite easy in D flip-flops. For JK flip-flops, which as I said before, they're most of the time cheaper compared to D flip-flops and other NAND gates. So in order to use JK flip-flops, you have to figure out the inputs, right? Because input and output relationship is not that simple in the JK flip-flop scenario. So therefore, you have to add extra columns here, okay? For the J and K inputs of the two flip-flops. That means you need 4 different columns here, okay? Unfortunately, I didn't use this space very well. So I'm going to just erase them because these are just, extra stuff that we use to calculate our Boolean expressions. Okay? Okay, so I'm going to now put JA. You've probably figured out what JA means. JA, KA, JB, and KB. Okay? These are the inputs of 2 different flip-flops. JA means the J input of the A flip-flop, the first flip-flop, and KA means the K input of the first flip-flop, which I usually call A. Okay? Now, what is this relationship? Now the question is, what is this relationship of these states and inputs? What should you provide here? So that's going to cause you this state transition going from 0, 0 to 0, 0. Okay? That's the question. Okay? So in order to do this, you have to use excitation tables. Excitation tables actually can be derived from the state tables given for these flip-flops. So let me just show you that real quick. Where is my state diagrams? Okay. In other words, characteristic tables or state tables, the same thing. I'm going to just show you here and then erase. So for example, for JK, remember this is in your slides. If J is 0, K is 0, QT plus 1 is QT. If J is 1, K is 1, you got a 0. If J is 1, K is 0, you got 1, and you got J and K1, both 1, it's Q prime T. But I don't need this, because I already have given AT and AT plus 1. This transition is already known to you. What you need is they reverse. What should be the inputs so that you got these outputs? Here is what you need. Okay, that is called excitation table. You need QT plus 1, right, as input. What is the corresponding J and K? This is 0, 0, 0, 1, 1, 0, and 1, 1. Is that a possibility? These are inputs now in your table because you have access to these now, right? You see, for example, here, AT is 0, AT plus 1 is 0. That's why I have these 0, 0 here. Okay, put in place of QA, and boom, you got AT and AT plus 1. The question is, what should be J and K corresponding to these Qs? Okay? So, for example, it's kind of easy to derive this table, but you don't need to derive it or memorize it. You can actually use your cheat sheet to copy-paste your excitation table, so you don't need to memorize. But I just want to show you how this excitation table derived from the characteristic table. Okay? So, by just looking at this, you see if QT is 0, okay, this is 0, right? Okay, this is 1, okay? And QT plus 1 is 0, so this is also 0, okay? So, you can see that in this case, in this particular case, if I see 0, 0, okay, the input J and K could be 0, 0 or 0, 1. These two cannot be, okay? So therefore, I actually put J to 0 because it's guaranteed to be 0. But K could be 0 or 1. That's why I'm going to say, don't care. Because it could be 0 or it could be 1. Both are possible. Okay?
How did you decide that?
Because K could be 0 or 1. You see, QT is 0. Q2 is 0. That means QT plus 1 is 0, 0. You see, QT plus 1 is 0. That means you're in here. Okay? In order to produce QT plus 1, 0, then you either have J0, K0 or J0, K1. J is always 0. That's why I put a 0 here. But K could be 0 or 1. So both can be. It doesn't change the QT plus 1. QT plus 1 in either case is 0. That's why QT plus 1 is 0. That's why I put a don't care here. Okay? And similarly, for example, if QT is 0, this is 0, 0, and QT plus 1 is 1, that means I have to look here, right? Because it's 1, 1. But if I look at here, J is 1 all the time, and K is, again, don't care. Similarly, if QT is 1, this is 1, and QT plus 1 is 0, this is 0, then I have got, this is 0, right? That means if QT plus 0, then I have to look at these two, right? Because QT plus 1 is 0. But if when I look at here, K is 1, J is changing. That's why J is don't care, this is 1, and this is going to start, you can also verify that it's don't care and 0. Okay? Similar, using similar logic. Now coming back here, final step actually, is that you have to figure out these inputs. So when you look at the AT, so I'm talking about the first flip-flop. So that means my QT plus 1 is AT plus 1. So when I see AT and AT plus 1, 0, 0, I come back here, I see 0, 0, the corresponding J is 0 and don't care. So I put it don't care and, 0 and don't care. Okay? And similarly, I have 0, 0. I have 0, don't care. I have 0, 1. When I see 0, 1, it's 1, don't care. I see 0, 0, which is 0, don't care. I see 1, 0. When I look at 1, 0, it's don't care 1. I see 1, 1. I got don't care 0. I got 1, 0. I got don't care 1. I got 1, 1. Oops. Guys, I'm actually shifted myself. So this is not wrong. This is wrong. 0, 1. Let me just check it quickly. It's 1x to read. 0, 0. 0x, though. That's true also. 1, 0. X. 1, 0. Yes, that's also true. 1, 1.
Don't care 0.
This is x0. I think that's true also. 1, 1. x0. That's x0. And finally 1, 0. which is x1. Okay? I'm just copying things, you know. I'm not doing anything magical. And you have to do the same thing for B. In order not to confuse yourself, maybe it's a good idea to use a red color and then draw these columns that are of interest to you. For example, you have to compare this and this. BT and BT plus 1. Now I'm going to use the exact same excitation table. I got 0, 0. 0, 0 creates 0x. I got 0, 1, 1x. I got 1, 0, x1. I got 1, 1, x0. I got 0, 0, 0x. I got 0, 1, 1x. I got 1, 0, x1. And finally you got 1, 1. Correct? x0. Okay. If you haven't done anything mistakenly, okay, this should be the K. This should be the inputs that should be provided to you to create those transformations, state transformations. Okay? That's why I said, JK flips are cheaper. However, in order to just use them in your design, you have to use these input-output relationship because the input-output relation is not that so straightforward as compared to D flip-flops. Okay? Okay, so of course, you already have, A, B, and Y. If you were to use D flip-flop, you would actually use these two Boolean expressions to draw your circuit immediately. Because D flip-flop says that input is just your next state. However, for JK flip-flops, you don't use these two, right? You actually instead use JA, KA, JB, and KB. And apparently there are many don't cares, so their Boolean expressions would be much simpler. Okay, but you have to, of course, draw 4 different Carnot maps. 1 for JA, 1 for KA, 1 for JB, and 1 for KB. So you got 4 different Carnot maps, and you do the minimization to come up with 4 different expressions for JA, KA, JB, and KB. I'm going to just draw with, how many minutes do I have?
More than 10.
More than 10? So maybe we can quickly draw them also. Okay, just finish things. So I'm going to just draw. Okay, so for JA, I'm going to use the same terminology, A and BX, okay? Okay, I have, for JA, I have 0, 0, 0. So I'm sorry, this one is important, which is 0, 1, 0. 0, 1, 1, 1, 0. So 0, 1, 0 is here. And I have 4 don't cares, as you can see, right? For all A. 1. So this is don't care, don't care, don't care, don't care. Okay? And apparently, maybe the most simple Boolean expression that corresponds to this column map is this, right? You don't need to consider the rest. Just set them to 0, because that's going to complicate your circuit. So A is gone. You got B, X prime. Okay? Okay, so this is your JA, right? So JA. Let me just draw it here. And let's just say this is your KA. This is your KA. In KA, I have, when A is 0, I have don't cares. Okay, all these don't cares. And there's this 1 here for 1, 0, 0. Okay, 1, 0, 0. And I have 1 here for 1, 1, 1. This is 1 here. Okay? Okay, apparently, unfortunately actually, there are 2 here that you can use. Okay, this one corresponds to B prime, X prime, and this one corresponds to BX. Okay, so you sum them to find JKA. So JKA. Okay. All right. I'm going to draw the other 2 Carnot maps maybe here. Okay, and these are for JB and KB. So for JB, you see I have don't cares for let me see, for B. For B is 1, right? Don't cares for B is 1. So this is 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. So this is BX, this is A. So B is 1, right? So this is don't care, this is don't care. For B is 1, don't care, don't care. So these are my don't cares. And I have one here, which is 0, 0, 1, 0, 0, 1, and I have another one here, which is 1, 0, 1, right? 1, 0, 1. Okay, good, because now these are kind of neighbor to each other. I can actually group them together to eliminate A and B, so actually it's an X. Okay? You already have come up with an X here, remember? Which is B plus. Anyway, so we got final KB. For KB, you may realize that this is don't care and this is don't care, which is B0, right? So this is, you see, B is 0. So B is 0 is, this is 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. B is 0 actually is these 4 places, right? All right? And finally, we have 1 here, and which corresponds to 0, 1, 0, 0, 1, 0, right? And I have another one right here, which is 1, 1, 0, 1, 1, 0. That's also good because these are actually neighbor to each other. So I'm going to just use this type of grouping, which corresponds to A is gone, and B is gone, right? But this is X prime. That's X prime. You see, kind of easy Boolean expressions result. In this case, you see, these are more complicated. For JA, I think it's just a BX prime. For KA is just B XOR prime, right?
Yes.
It's B XOR prime. So B XNOR.
XNOR.
Actually, B XNOR, right? It's also a single gate. So, and this is X. This is X prime. So these are kind of very, very quite easy to draw. So if you're okay, I'm going to use a couple of more minutes to draw the circuit and then let you go, all right? So let me just erase this.
9 minutes.
Huh? 9 minutes? Okay, so we're basically efficiently using the time. That actually made me smile. Good. We're on track and we're on time. Okay, so let me draw the circuit as a final step, of course. All right? Okay, so I have X, T, input, this input, right? It's coming in. Remember, we've designed a circuit that is useful, actually, that detects a specific pattern, okay? So now I'm going to draw that circuit that does exactly this job. So X is actually going into now to our circuit, but I have to, of course, calculate these JA, KA, JB, and KP. But before that, I'm going to first put my flip-flops. Okay, those are JA, KA. Okay, and this is A prime, right? And I have JB, KB, and this is B prime. So I put the JK flip-flops first. Now I need to, of course, calculate those. For example, JA is BX prime, okay? So JA is going to be BX prime. I have X, maybe I will need an X prime already, so I'm going to just roll this and X prime is here. And I need B. So B and X prime now go into an AND gate, right? To generate the corresponding JA value. Okay? And what is KA? KA is just the XNOR of B and X. So I already have a B and I have an X. So maybe I can put an XOR here. Okay? And then connect it to X. And the other connection, oops. I already have a B here, so I don't need to really prolong my wires. Put just a dot here to connect it. Okay? But this is, of course, XOR, right? So I'm going to put a small circle to make it XNOR. Okay? It's pretty simple to make it XNOR. So I got an XNOR for KA. Okay, we're done with the first flip-flop. Let's just look at the second flip-flop. Okay, shall we? So in this case, I have actually a very simple Boolean expression. JB is X and KB is X prime. Pretty simple. The JB is X. I already have an X. And I already have an X prime, right? So I could actually take X and X prime to the corresponding inputs of the JK flip-flop. Okay? All right. Finally, we already have a Y, but we already know what Y is. Okay? We don't need to really transform Y because Y is a function of states and the inputs. State meaning that A, B, okay, and X. So I already have an X here. Okay, and this is my, all of them are AND gated, and this is your YT. That YT is going to tell you when will you have this pattern that you're looking for in the sequence appears. Whenever Y is 1, that's going to tell you I've figured out a pattern in the circuit. I mean in the sequence, sorry. Okay? All right, so you can see that you might have done this using a D flip-flop. Okay? If you're done this in flip-flop, a D flip-flop, you would use this expression, which is more complicated, and this expression for B plus X, which is almost the same complexity, and this is also the same. However, this one is more complex, apparently. All right? So the JK flip-flop, when you use JK flip-flops, of course, this example is quite simple. Okay? Particularly the sequence that we're using only 4 bit long. In practice, we usually use 20, sometimes 30 bits long. Okay? So the patterns are usually longer. And that would make your circuit, of course, more complicated. The gist of the main idea here is that when you use JK flip-flop, you reduce the number of dollars you're paying. Okay, that's first thing. The other thing is that the circuit that you're adding as front end and back end are simpler, typically simpler. In this case, that simplification is quite not very clear. However, in bigger examples, more complex examples, you actually can observe that. Okay? Any questions? By just looking at this circuit, could you be able to say that it is actually detecting 1011? No. Okay. That's why you're learning about the design. Okay? All right. I think we can finish today's class then, if you don't have any questions.